And finally, let us summarize the material that we've learned today. So today we have covered linear homogeneous systems of differential equations when the matrix has constant coefficients. Alright, so to do this we need eigenvalues and eigenvectors, and hopefully there are linearly independent eigenvectors. Right, and then every real eigenvector, it gives us one possible solution, and every pair of complex conjugate eigenvectors, it gives us, well, a pair of linearly independent solutions. So the correspondence is 1 to 1 still. So then we are going to get n linearly independent solutions, and hence the general solution is going to be the linear combination. This is if the matrix is diagonalizable. If it is not, then we're in trouble, so you have to read the textbook if you want to find out about it. But anyway, so we have covered a lot of different types of phase portraits, and they are distinguished by the whether, well, in case of this is when that there are two equations with two unknowns. So they're distinguished by the signs of the eigenvalues if they're real, or by the sign of the real part of the eigenvalue if eigenvalues are complex. So the unstable node, saddle point, asymptotically stable node, unstable spiral point or spiral source, center point, and asymptotically stable spiral point or spiral sink. Okay, then there could be more phase portraits which we did not really cover, just very quickly looked at. Unstable proper node, stable proper node, improper node, and, well, stable and unstable. So what we did not cover at all is the case when the determinant of the matrix is 0. So which means that one or even both eigenvalues are zeros. So I suggest that you try to figure it out by yourselves. Well, and finally, if we have a nonlinear system, then sometimes it is possible to calculate trajectories of a nonlinear system explicitly. And that's all for lecture 10. In the next lecture is the last one, we are going to work with nonlinear systems more closely, and we are going to see how we can analyze types of critical points for nonlinear systems applying the methods for linear systems.